Hey, this is a video for 4.5, Intermolecular Forces. So go ahead and set up a new entry in your Cornell notes. Remember to start a new page for this video. Also check out the essential vocabulary. Today we'll be discussing polarity, symmetrical, and hydrogen bonding. So polarity is the unevenly shared electrons resulting from a difference in electronegativity. So when we're sharing electrons in a covalent bond, they're not always shared evenly. So sometimes the more electronegative element will be pulling the electrons towards it. So if the difference in electronegativity is greater than 0.5, it will be a polar bond. Here's some examples. So this is an example of a nonpolar bond resulting in a nonpolar molecule. We have oxygen. So this is what oxygen looks like. Remember, it's diatomic and it has a double bond between the two oxygens. Each one is 3.4, so each one is pulling. In other words, there's no net pull, so neither one is basically hogging the electrons. That is resulting in a nonpolar bond and a nonpolar molecule. Another example of a nonpolar bond and a nonpolar molecule is methane. We have the carbon, we have the hydrogens. And the carbon is 2.6 and each one of the hydrogens is 2.2. The difference is 0.4. So there is a slight pull, but it's very, very minimal, so it's actually not considered a polar bond. So carbon and hydrogen, anytime you see that, will be a nonpolar bond. And because this only has nonpolar bonds, this is a nonpolar molecule. So this is an example of polar bonds. We have the carbon, we have the oxygen. Carbon is 2.6 electronegativity, oxygen is 3.4. The oxygen is pulling the electrons, so the electrons are spending more time around the oxygen than they are around the carbon. That's because oxygen is more electronegative. However, because there is an oxygen on each side, it is balancing out the polarity. So even though the bonds are polar, because this is symmetrical, it is a nonpolar molecule. So symmetry, remember, means that it's the same on both sides. Remember that from algebra or geometry. Or you should just know the word symmetry. This is a symmetrical molecule. The charges are canceled. So it's trying to pull the electrons, but it's not succeeding, again, because of symmetry. So this is how they will draw it in chemistry. This basically implies that this is where the plus charge is, and it's going away from the plus charge towards the negative. Now this is an example of a polar bond and a polar molecule. So I talked about this before. This is 2.6, this is 2.2. These are all nonpolar bonds. However, this one is polar. So most of the electrons in the carbon, a lot of the electrons are going to be spending a lot of time around this chlorine, which means this chlorine is going to have a slight negative charge. This is not symmetrical because the chlorine is not balanced by something over here. So we have three areas, three nonpolar bonds, one polar bond. This is going to be a polar molecule. So there's going to be some practice that we do in class, but a general rule of thumb is you can look at these molecular shapes to determine polarity. So I've done this little sketch, and these represent nonpolar bonds. This would be like the methane I showed you. If the polarity is so close, but the elements are different, it's going to be a nonpolar bond. And because these bonds are all nonpolar, it is a nonpolar molecule as well. This would represent a diatomic. Anything diatomic is automatically going to be nonpolar. And this is an example of something that shows symmetry. So because this shows symmetry, these polar bonds actually would be a nonpolar molecule. Now these polar molecules, if we have two elements bonded, but one of them is pulling the electrons towards it, this is definitely a polar bond. This will be a polar molecule. None of these are symmetrical. So because they have a polar bond, they will also have, the molecules will be polar. My color scheme, red represents polar bonds, blue represents nonpolar bonds. So if you have a mixture of polar and nonpolar bonds, you got to look to see if it's symmetrical. Now, what does this all matter? Well, these intermolecular forces, inter means between. So these are forces between molecules. And this really comes to play when we see hydrogen bonding. And hydrogen bonding is the attraction between positively charged hydrogen atoms and negatively charged atoms in nearby molecules. We really see this with water. So because water is oxygen is very electronegative, it's pulling the electrons from the hydrogen. So when you look at a water molecule, this is basically just the atomic structure using like the little balls that you'll use in chemistry. But you're going to have positively charged hydrogen because the electrons are spending more time around the oxygen. So when you see hydrogen bonding, these hydrogens are going to be positive and they're going to be attracted to the negative oxygens. So you're going to see the water kind of sticking to itself. So hydrogen bonding is an example of an intermolecular force. Whenever you have polar items or polar molecules, they will definitely behave a certain way in water. Water is very polar. It is probably the most common polar molecule that we have. Now, this will come into play in future topics, but for right now, you should understand that intermolecular forces are forces between molecules because of the differently charged atoms within that molecule. And this really comes into play when we're talking about ionic compounds. So we have sodium chloride, and this is very soluble in water. Sodium chloride is a very strong bond. Ionic bonds are very strong, but when you put them in water, water can easily break them apart because of this hydrogen bonding, because you have this polar molecule. The negatively charged oxygens are going to orient themselves around the positively charged sodium ion, and the positively charged hydrogens are going to orient themselves around the negatively charged chloride ion. This will come into play in future topics. This is just an introduction. I want you to respond to this check for understanding. I hope that this video was informative. I thank you for your attention, and I will see you soon.